So in the last class we saw the read failure. One way of dealing with the read failure is to actually make sure that during reads the read current doesn't go into the cell, because when the read current goes into the cell, the current when it goes into the cell, the side where the node voltage is 0, it causes this voltage to go up because there will be an IR drop across this transistor, and so that could cause this following inverter to trip and it can fail. So one solution to that problem was to actually put a separate read buffer, so that when you read the cell, there is another read bit line and another read word line, and this read bit line is P charge high. When you access the cell, you turn on the read word line, which turns on this transistor, and then if this node value is 0, this is off. So bit line holds the data, holds the potential. So you read it as a 1. If this value is internal node voltage is high, the read bit line discharges, and so you can sense that. So this is the 8T cell which separates out the read current into the from going into the memory. Notice that there is also a dual ported memory. The ports, if you had a separate decoder for read word line and write word line, then you can have 2 ports, independent ports, one to do writes, one to do reads. In the same cycle, if the 2 decoders could be operating in parallel, as long as they are not decoding to the same row, it is fine. Right? You can have a write into one row while read from another row. This is very useful for FIFOs. If you are building a FIFO, first in first out type memory structure, like a queue is another name for a FIFO, where someone is reading from the front of the queue and you're also putting into the back of the queue. So you can use this kind of structure to do that. But for generic SRAMs, the problem with this structure is basically the area overhead, because you have from 60 you went to 80 along with 2 additional lines, one vertical bit line and horizontal word line. Now one of the things is that in a memory, if you go back to how a memory is organized, you have cells arranged in a 2D matrix, right? So the word line goes horizontally to turn on all the cells in a particular row, and the bit line is vertical, and all the cells in a column are connected to that bit line. They are connected through the access device, either this one or this one. So the corner condition for a read, when you are doing a read, imagine that you have a lot of cells here, right? And say this cell is holding a value which is opposite of the value for all the remaining cells in that column. When the leakage is very low, it doesn't matter. None of the only one word line is on, let us say the top word line, and all the remaining word lines are off. So all these cells are supposed to be disconnected, and you don't really care what is there in the other cells in the column. But when we are talking of sub-threshold, or also any process where leakage is high, deep submicron process, maybe leakage is high, then you have to worry about, even when my word line is off, that means this word line is 0. So this is supposed to be off, but notice that this bit line, when it's at VDD, and say this is ground, then I have a large VDS across it. So I can have a lot of leakage current going out here from the unaccessed cells in that column. So if I have a long column, except for one cell which is accessed, everyone else is unaccessed, but all of them will be leaking. And the worst case condition is when this one is supposed to be a 1, whereas everyone else is 0, right, holding a 0, such that, basically the idea is that everyone else is pulling leakage current into it, whereas you're not, and causing the bit line to fall when it's not supposed to fall based on the data. So that is the case you have to essentially design for and make sure you're able to overcome that particular case. And because of that, what you end up doing for very leaky processes, or when this is a problem, is that you end up having a very short bit line. That means you don't put too many cells in that column. So you might have a bit line column of 8 or 16 cells, right? So one cell is accessing, remaining 15 are supposed to be off, but they are leaking. So ensure that your design works correctly with that condition. So when you do that, you end up with short bit lines, but then every group of, so that is called a local bit line because it's connecting locally to the cells out here. So let us say in this case there are 8 cells. So this is your local bit line, but you have a very large array. So you can have a global bit line. This picture is not correctly representing that, but you can imagine that there is another global wire which is running on top, and every group of 8 locally connects to that global wire. So when you do that, you will have some circuitry here, some sensing and some drive and so on. So that adds to area overhead. Every time you partition and create a local bit line, in between groups of local bit lines, you have to put some circuitry. So that adds to area overhead. So every time you partition a big memory into smaller chunks, area overhead increases. So not only have you gone from 60 to 80, increase the cell area, in addition you have to also deal with this large partition, right? So the overall area for sub-threshold memories can become quite large. So to address that problem, these researchers from MIT have proposed this 10T cell architecture where you have kind of paradoxically increase the cell area even more. Instead of just having one M8 and M7, they have put and 2 additional transistors, an M10 and an M9. And the hope is that the motivation for this is that they want to reduce the leakage of the off devices. That means when read word line is off, they want to reduce the off cell leakage. When they do that, they can have much larger local bit lines and so hope to recover the area back. If you didn't do this, you have to partition a lot more, but if you did this, you partition less and so you recover the area back. So that is the intent for this. So how does this work? So you have 2 conditions. When QB is equal to 1 or QB is equal to 0, these are the 2 possible values the memory cell can store, right? So QB is the internal node from the 60 cell. So when QB is equal to 1, M7 is on, and so what they have done, this is the problem condition, right? If you didn't have M10 and M9, then you would have an on M7 and an off M8. And if all the cells were off cells were like this, all of them had a QB equal to 1, you'll have only a single off M8, a number of them. Let us say you have 256 cells, 255 off M8 transistors which are in parallel pulling down through leakage the bit line. So to reduce that, what they have done is they have done 2 things. One is they have put M10, which introduces a series stack out here, right? So what that does is that whenever you have this kind of a right, so that is one. The second thing they have done is also put an M9 out here. Now M9 is off, but still there will be some leakage through M9, what it does is this internal node QBB then is pulled up a little bit more. When QBB goes up, the gate potential, see the voltage of RWL is 0, right? We are looking at an off cell, whereas the source, this is the drain for M8 because current flows like this. So the source goes up positive, and so the effective voltage across gate source voltage will be negative, helps to make the transistor even more off and reduce the leakage.
But here if M10 is also leaky and it's more leaky than M9, then it will not go to high voltage.
Correct. You look at the condition when you didn't have M9 or M10. Compared to that, this will be better. This voltage will be higher than what it would be if you didn't have these 2. But what voltage this will go to, right, that is very difficult to predict. It is open because that voltage is set by the relative drive strength of M9 and M10, and that is going to vary a lot across due to process variation. Even within die variation, cell to cell, there can be large variation. That you are trying to, when matching a PMOS threshold and NMOS threshold is always a tricky thing. At least you try to, if you have to match thresholds, try to match it for 2 NMOSes or 2 PMOSes. But matching P to N can be even worse. Okay, so the question which is being asked is, will gate induced drain leakage, GIDL, have a problem? I mean, have a impact on the leakage out here. So, what is gate-induced drain leakage? So, gate induced drain leakage is when you have a small accumulation region which happens and there is leakage because of that, right? So, yes, so that if that leakage current goes up, that will have an impact. Similarly, the tunneling current from the gate, the channels, not channels, the gates will also be an issue, but those are things which you cannot do much. Now if you come back to the gate induced drain leakage, see, we are not saying RWL is negative. um, uh, you're not making it more negative, right? What you're doing is actually taking the source of this transistor and making it positive. So you're making the effective gate voltage here, gate source voltage negative, as opposed to the gate drain voltage.
But in the when we studied, even the we studied for the same purpose that if we wanted to reduce the leakage of a transistor, we try to make it negative, but it will have an adverse impact.
Correct. That is when you make the gate voltage more negative. We are talking of the gate source voltage out here.
It's not the same.
Correct, absolutely. The GIDL is gate induced drain leakage. It's a gate to drain potential.
This VGS negative will not be the same.
Correct, exactly. So the source of the transistor is here, the drain is here. So the source going up positive makes VGS, VG is 0, source is also 0, but it could go a little bit positive. So then VGS becomes slightly negative. Whereas what the gate induced drain leakage is between the gate and the drain. In the case when QB is 0, you have this off and you have M10 and QBB M9 helps. Now in this case M9 is on, well, relatively on. So this voltage QBB is closer to VDD. So you reduce the leakage out here. And this leakage, so you can also have leakage like this, right? That is just a leakage due to that will lead to power loss. Whereas this leakage can lead to functional failure. Leakage through the access device, with a lot of them adding up, can lead to functional failure. Whereas leakage from out here is essentially more power loss. It won't lead to functional failure, it's just you're just burning more power. So both here and here you have two series of transistors, so that helps to reduce the leakage essentially. So this is basically the concept which they have proposed, and I want to show this graph from their paper just to illustrate the kind of analysis you will have to actually do. Suppose you were asked, what should we do? Right? Suppose the question was asked to you by a manager. Okay, we are designing this IP for a new SRAM macro. Please tell me what we should do. What should be the configuration? Right? So you have to actually go back and do analysis and try various combinations for each one. You have to have a quantitative as much as possible, some numbers to back up whatever you are doing. Right? So that is the scientific approach. Use data-driven decision making. It's not always possible. At the end of the day, you might not have full data, but still it helps to improve your decision making. You have more confidence in your decision. So here what they have done is they have done analysis across all different corners. W is weak in their nomenclature, S is strong. So they have taken a weak corner. That means both NMOS and PMOS are weak. And the circles are for the 10T transistor and the squares are for the 6T transistor. So here what they have done is they have taken the 60 transistor with different number of bit cells in the column, 16, 32, 256. And the solid lines are for the case when you're reading a 1 out of the cell. That means the bit line is supposed to be at VDD. So this is all for a VDD of 300 millivolts. whereas the uh, whereas the dashed one is for the case when you're reading a 0 from the bit line. And so they do a simulation where they let the bit line split. Once it settles, they're then recording the value. Let us say you're doing analysis at 120 degrees, you record, and you're doing it for a 256 cell situation. You do a simulation, you see, record the value for what is the high voltage. If the cell was reading a 1, this is the voltage you get in the bit line. If the cell was reading a 0, you'll get a different voltage. You see that in the case of 256 bit cells per bit line, it doesn't work. The memory will not work because the high one is lower than the low one. So it basically will not work. Things improve with 32 and 16. But when they go to, that is because again, it's really the problem is happening with the high one. As you increase the high one, as you reduce the number of cells in the high one, when you want to read a 1, the opposition to reading a 1 is reduced. Why? Because only 15 other cells are leaking. Here 31 cells are leaking with the opposite value, 255 cells are leaking with the opposite value. So all of them are trying to discharge the bit line. Whereas here so this improves because of that. But still you see the supply voltage is 300 millivolts and their bit lines are pre-charged to 300 millivolts. But then when you read a 1, you just get this, about 150 millivolts or so. So what they say is when they go to their 10T cell, they are able to pull up the voltage of the 512 cells. But even as the temperature changes from 120 to minus 40, that high value still does come down because of enhanced leakages and so on. But still they are able to maintain a margin, and so this is basically how they are concluding that their 10T approach allows them to pack more cells in a column, so you partition less and hence the area overhead is reduced. Basically the when you say okay, so the question is at low temperatures don't you get a proper output? Now of course, what is proper? Proper is that if you're expecting, yes, ideal value you will not get because of leakages and so on, right? It won't be a proper digital value, but there should be enough separation between a high value and a low value. If there is enough separation, correct. So now the temperature, what does it do, right? As you reduce the temperature, your threshold voltage is supposed to increase, right? But your subthreshold slope sharpens. So, so you have those two effects going on out here. The subthreshold slope sharpens, but the threshold voltage is shifting, and and the mobility also goes up, right? So the off current is basically mu times e to the minus Vt by nVt, right? Vt thermal voltage is reducing, threshold voltage is increasing, right? And when we say subthreshold slope improves, that means it sharpens, that means the thermal voltage is coming down, that is why. But the mobility also goes up. So all these, there are two things which are increasing the current, one thing which is reducing the current. So all these three things are counteracting. And in this case, the leakage is basically preventing the voltage of the bit line to be fully at 3. See, out here it's at 300 millivolt, whereas at minus 40 degrees, even with the even with the 10T cell, the voltage is not at 300 millivolts. It's actually lower. So the leakage currents seem to be going up in that case, right?
So 60 is better than 10
Yes.
60 is 60 is giving you a better volt. better low voltage than the 10T0. Correct. And what is the reason for that? Because what is a zero? What does it mean to say 60-0? 60-0 means the cell, because we are reading a 0. No, wait a second. So the bit line should be discharged to ground, right? So that means this is the case. QB is 1, it's supposed to be discharged to ground. Now, all the other cells in that column will try to charge it. I mean, will be opposite value, right? So that means all the other cells will be in this case, QB equal to 0. When QB is 0, PMOS is on. So you have, in the case of a 10T cell, you have the situation that the off cells are supplying current into the bit line. You don't have that problem in the 60 cell, because 60 cell also, let us see, in the case of 60 cell,
They all will help, some of them will help to research.
right. Even in the case of 60 cell, you can have the cell which is discharging will pull the bit line low, but the off cells can have a value which is opposite, and can, because of the leakage from the PMOS cell VDD, it can be putting current in this direction out here, right? So M4 and M5 are off. So M6 is, the current will split between M4 and M5 in the case when BLB is 0, in the case of 60. Here what happens is that, so it's very interesting. In the case of a 60, let us take the cell where all the other cells, okay, which are opposing this, the cell I'm reading. So M6 is on in an off cell, the cell which I'm not accessing, and M5 and M4 are also off. So the current from M6 is splitting between M4 and M5. So part of the current is going into the bit line to try to charge the bit line up. Now in this case, M9, part of the current goes to bit line, the remaining part comes here, but then there is a series stack out here. So the current going down is reduced, so more of the current gets diverted on this side. So because of that, the 10T cells are actually pumping more current into the bit line during the 0, the other cells. So that causes this voltage to go.
10T cell, we have a stack of 3.
Huh.
Which we are accessing. There is a stack of 3 which tries to discharge this bit line. So maybe because of the 3 stacks, discharge is not.
No. We are talking of this case, right? The case when you see these circles are higher than the squares. So what does it mean? That means, and what is that representing, right? That is the case when the cell I want to access has a value of 0. So it is driving the bit line to 0, right? That is what I want. That means the cell I want to access is discharging the bit line, the access cell. So that is good. But the cells which are not turned on, the remaining cells in the column, there what happens is that the bit line, for them, they see a bit line of 0. Okay, and let us say their data which they are storing is such that the PMOSs are on for all of them. So now the PMOSs there will be current from the PMOS, and this is 0, so there will be some current trying to go in here. This current splitting will be more because on this side there are 2 series transistors. So more current, leakage current will go here than here, and so because of that,
Whatever cell is on, in that case there will be C1 stack, no, so in that case you will also see it more drop.
Yeah. So correct. So okay, so the point being made is that the cell which is on is also the drive strength of that cell is reduced because you have 3 NMOSs in series which are trying to pull down the bit line. So the on current is also less to pull down, as well as the off currents will be a little bit more, and so
The transistor size for a 16 and 20 around the same.
it will not be the same.
So that
will be different. Not, yeah, it won't be drastically different. I mean, they'll be slightly different. See, the thing is, in the case of 60, if I'm see, you don't want to make these transistors too big also. All of the transistors in SRAM will be anyway close to minimum size because the overall area of the SRAM has to be kept small. So there will be some difference, but not too much. Okay, so basically two reasons why this is higher for the 10T than for the 60. One is that the on cell current is lower because of series stack of 3, and second is that off cell current is also higher because of the same problem, that there are two series stack on this path whereas one out here, causing it to go a little higher. I would basically say it's the current from these off guys is more of the reason. The thing is that a series stack, all it does is helps to reduce it increases the time of discharge. If I had no leakage, then it will eventually discharge to ground. Okay, so that was the right. In the case of a read, that was a read. In the case of a write, how do you write into the cell? Right, you have bitline and bitline bar, and let us say V2 was high and V1 was 0 before you did the write, and you want to change the content. That means you want to pull V2 low. So what you do is you turn on the word line and bitline bar is kept low so that V2 is discharged. And when V2 discharges, it comes low enough that you trip this inverter and that writes V1 gets pulled up and then you write into the cell. That means you want to make sure N4 is stronger than P2 so that this voltage comes sufficiently low. So that is basically what you have to ensure. When you have a write failure, what happens is that V2 doesn't come low enough. It doesn't come low enough to trip this inverter, and then when you turn off the word line, it just goes back to holding the same data. Okay. So that is basically why write will fail. So you really have to ensure that N4 is stronger than P2 across all the process variations and all corners and so on, for you to get reliable data. Now, how do you ensure that, right? To ensure writes will happen. So now you know what is the cause for the failure. So how to fix it is basically somehow you have to make the relative strength of N4 more than that of P2. And there are many different ways of doing it. And these circuits which help to do that are called assist circuits. Write assist. Similarly, in the case of the read, any external circuitry used to help the read, they're called read assist circuits. So, for example, maybe you boost the word line a little bit more during a write so that N4 becomes stronger, perhaps. The other thing which is done is P2 is weakened even more. How is P2 weakened even more? The supply voltage of P2, the cell, is reduced. It can be reduced in two ways. Actively, you reduce it to a different voltage. You might have two voltages in the chip, a higher voltage for reads and holds, and a lower voltage for writes. So you can, just for that duration, you can connect the cell supply to the lower voltage, and the cell finish the write and pull it back. In this approach, what the authors, again the same authors, Calhoun and company from MIT have done is that they don't pull the cell VDD to a specific lower voltage. Why is that? Because then you need to generate that specific lower voltage and supply it. So what they do is they just disconnect the cell VDD. They have a PMOS pulling the cell's VDD to, through this. They just turn it off. When they turn it off, what happens is the VDD floats for a short duration. And there is anyway leakage, right? Leakage causes the cell voltage to start coming down. And then you basically, that helps to do the write, and then you pull it back up. So this is called a virtual VDD. This is very similar to the power gating concept, right? You can also notice that this is like a sense amplifier, inverted sense amplifier. A cross-coupled sense amplifier has, if you remember from you had a cross-coupled NMOS PMOS pair with a gating NMOS transistor. This the same structure except there is a gating PMOS transistor.
In line you are switching off VDD or so you can I mean the one will be rounded to zero, but at the same time QB also won't get any voltage. That means it has to be timed.
Okay, so the
That
question
not come to one, so
question which is being asked is that when you shut off VDD on and disconnect the virtual VDD, the virtual VDD will start falling. Now, when I want to write into the cell, let us say I want to write a 0 into Q and QB was high, what I'll do is bit line will be 0, which will causes Q to fall low. When Q falls low, Q was high and QB was low. Sorry. So when bit line is 0, Q will start falling low, and you would want QB to go high. Now QB will go high only up till the value of virtual VDD. It won't go higher more than that. So so the question which is being asked is the timing of this critical? Because what if you don't turn on the virtual VDD very soon, right? I mean, how critical is it? Clearly, if you leave it floating for too long, that is bad because everything will discharge. But question is, how critical is it? I mean, do I immediately have to turn it on after the word line goes low, or what do I do, right? I would say the answer is that it's not very critical in that sense, because the virtual VDD will be a large capacitance. It will be there, so it will slowly come down. This will go up, yes. It will, hopefully it will not go up. I mean, QB will go up to virtual VDD value, and and you just turn it on. You might have 1 or 2 gate delay difference between word line and this thing, so that I wouldn't expect it to be too critical.
so in that case only NMOS and NMOS need to be on and off. Will not be to be on and off in case QB doesn't have a good idea.
Right. So it won't be. You're right. So this is, you don't want to be in that.
Again, the Q will be floating there in that.
Correct. No, the point is that the Q and QB will, you clearly don't want virtual VDD to be floating for too long. The only thing is, it doesn't have to be, I'm not saying that you leave the virtual VDD floating for, many gate delays.
So my actually point is that would it be a transient sort of thing that when it is going down, then subsequently that should also start coming up, so that when it is totally zero, or when the word line goes off, then the NMOS should be on properly, and the PMOS should be off, and for that QB has to have good.
The thing is that the question is basically, when the word line goes off, shouldn't this NMOS be properly on, so that it will hold this value at ground, and right, and this, yeah. So see, the way to think of it is that this is like a sense amplifier, right? And when the word line, when you turn on this PMOS, you are pulling this back virtual VDD which had come down back to VDD, and so you are amplifying whatever is there. Yes, it won't be a full digital value after you finish the write, right? Because the virtual VDD is not fully at VDD. But as this pulls up, then it will restore the thing. So because it's like an amplifier, which will amplify and restore the value.
So one more point. There is charge coming from the bit line versus transistor. Let me pull it up to VDD. Bit line is charged to 1 and access transistor is 1. As soon as NMOS shuts off, that point will be put
Correct.
to 1.
So the question which is being raised is, want QB be pulled up to VDD through this NMOS transistor? But the thing is that it won't. This NMOS transistor is, I mean, this has been designed in a way such that the drive strengths are such that
But we wrote 0 on the Q. We brought Q down to 0. This NMOS is not off.
This NMOS is off.
Yeah, because we brought 2 0.
Correct. So this, so this bitline bar also helps to pull up QB. Because this bitline bar is there. Correct. So this also helps to pull up QB. And then you have some more margin where virtual VDD can be, you don't have to have very precise timing of word line and pulling up this virtual VDD.
Isn't this virtual VDD supplies how many rows? Just 1 row or multiple rows?
So now that is correct. So now that is the important point out here, is that in this architecture, the virtual VDD line is going horizontal along with the word line, which means that you cannot do bit interleaving. That means all the words in the row have to be written or read. Now, lot of memories, what you do is you have a column mux. Right? You do interleaving of bits from different words, at least 2 to 1, 4 to 1, 8 to 1, depending on. That has a benefit also from a distinct perspective, soft error perspective, right? Because when a particle hits, ionized particle enters the cell, it can flip. What it does is, as the particle goes through the silicon crystal lattice, it breaks the bonds, creates electron hole pairs. The electron hole pairs will diffuse in a small geographical region and cause excess charge to come into bunch of cells which are called close by. Now, if the cells all belong to different words and you flip the bits of the cell, then the errors, you are making it into single bit errors. Yes, you have 4 cells flipping, but the 4 cells are all consecutive and each of them belong to a different word. So as far as the word goes, it is still a single bit error. And so a simpler code like a single error correcting double DED code will be good enough to fix it. So the interleaving is very important from that perspective for robustness, because you are spreading a burst error into single bit errors. So you cannot lose that property out here when you do the horizontal VDD. So the other way is you can have a vertical VDD, and so that will allow you to do interleaving. So there is one more paper I'll put up. I don't have that reference here. I'll discuss in the next class, which has a small survey which compares the pros and cons of different schemes. So you can have a look at that paper and get a better sense for what are the pluses and minuses. But basically, horizontal VDD is not compatible with bit interleaving. Okay, so anytime you have a memory, in general you have this problem. Whenever you have an array structure, it can be with any kind of array structure. It could be an array of pixels in a camera. It could be array of cells in a non-volatile RAM, etc. You have the problem of half select. That means because of the structure of the array, you turn on a particular horizontal line or a vertical line, depending on you kind of activate cells all along the row or all along the column. Right? Now, for full activation, you would like to have both a column and a word together somehow, the intersection giving you the access, so that's full. Whereas, so that you can uniquely pick up a particular cell. Whereas all the other cells in the column or in the row would be half selected. So that is called the half select problem, which is there. Any array structure, you will have that kind of a problem. Right? So there are various ways of dealing with it, and one way to deal with it is to use these access transistors and so on. But in general, that half select problem comes and manifests itself in different ways. So here is another approach to do the write, and this is a 10T cell from which was reported by Intel in one of their processors, ISSC 2012. So the read portion is the same as what we have seen, right? They have used a read buffer, but you see the cell they have changed a little bit for write. They do single-ended write into the cell, and they have this is pretty much like a standard CMOS latch, right? You have a feedback latch which has these transistors, which are, during a write, you disable these transistors, this one and this one, so that this node can be easily written by the bit line. And then you also have a full transmission pass gate structure out here, NMOS and PMOS in parallel. So this is the structure they have used so that they can easily do writes, and then for read stability they put the read buffer. So this is also a 10T cell. Of course, in this case, you might not be able to stack too many of these, because unlike the previous paper 10T cell, the leakage will be more out here. Right? So okay, any questions on this?
In the previous case, would it be possible that instead of a virtual PDB that doesn't have anything, we have a diode drop?
Correct. So the question is, can we not, instead of fully turning off the PMOS, have at least an NMOS with a diode drop? The idea is that this VDD then will be prevented from going all the way to ground and destroy it in case there are some issues where your timing is not okay and you don't pull it up fast enough, or leakage is too high, and by the time you pull it up it just goes. And that is actually done. So that is a good suggestion. And the thing is, the diode drop doesn't work well. See, these voltages, they are talking of 300 millivolts. So in this kind of scenario, having a diode type, that means having, what is a diode type structure? Essentially a NMOS gate, NMOS transistor with the gate connected to the drain, and that is connected. So that approach is used to in higher super threshold designs, I mean where the voltages you're talking of is higher than 300 millivolts. Yet you want to achieve robustness of write and allow for this virtual VDD concept. So there you can use the diode so that it clamps the virtual VDD from going too low.
Then we will use two MOSFETs.
You will have two of them in parallel. Okay.